Okay, so since it's time to start class and since I'm now recording, I want to ask if anyone has any questions about, before we get to just arbitrary questions, I will say that I have not made too much progress on the grading. I've graded something like 2 problems of the 7. So I would imagine that I'll finish the grading for your test by, Friday. So still a ways away. Don't worry, it's not because the problems were so tough to grade, it's because I have other grading responsibilities. I also grade for a grad class and they had a test this past weekend. So I just had lots of grading to do and I couldn't spend too much time on our class. That's all. I want y'all to be able to have your scores so we can discuss and chat. That's the best thing about math, is talking about it. Okay, any further questions before I begin lecture today? And I'm recording, okay. No, it seems y'all are on the quiet side. That's okay. So today's an exciting day, today and Wednesday. These are exciting days. So recall, last time we discussed the following topics. Last time we discussed injectivity of functions, surjectivity, and bijectivity. Is there a question? I just heard someone speak. No? Okay. So can someone remind me at least of the ideas of injectivity, surjectivity, and bijectivity, even if you don't give me the full definition?
So with injectivity, isn't it every element of the domain points to a unique element in the codomain?
That's right. So I'll draw a picture of what doesn't happen with injectivity. What doesn't happen with injectivity is 2 different elements getting mapped to the same element. Does not happen. Right? This is the picture that doesn't happen if you're injective. Here we had 2 different distinct elements of the domain mapping to the same element of the codomain or the range. Right? So this is forbidden if our function's injective. And what about surjective?
For every element of the codomain, it has a value in the domain that points to it.
Exactly. Everything gets hit, so to speak. Everything in codomain gets hit. Or in other words, the codomain is the same as the range, right? Usually we understand the range as a subset of the codomain, but surjectivity says those are actually the same set. And then bijectivity is just the combination of both injectivity and surjectivity for a function. And we noticed at the last time, we noted, although we didn't prove, that for a function, f from a to b, which is bijective, if a and b are finite, then the cardinality of a has to be equal to the cardinality of b. This isn't a very well written sentence, sorry about that, but I think that the point is still clear. If we're talking about functions between finite sets, bijections can only appear when the cardinalities of the sets are exactly the same. This is something that we kind of remarked on at the end of the last lecture. So does anyone have any questions for where we are right now with this? Okay, so what I'm going to do today is I'm going to introduce another operation on functions, and this will give us another perspective on bijections. So another operation on functions. And this will bring us back towards bijectivity. So what I'm going to do is I'm going to let f be a function from a to b. So yeah, idea. Let f from a to b be a function. And then let g from b to c be a function. Let me, does anyone have an idea of some operation that I can do that combines both of these two pieces of information, namely a function from A to B and a function from B to C?
Could you do f composed of c or g?
Exactly. A very natural notion is the composition of these functions. I can compose these functions. So now I define from these a new function called the composite function, which is going to be g composed with f. So the later function comes first and the prior function comes second. So g composed with f will now be a function from a to c, and it will be defined by sending an element a to what?
To an element c?
Yes, but it's going to be sent to a specific element C that are depending on, let me write this. Here, A gets sent to f of A, and B gets sent to G of B. This isn't telling you any new information. I'm just giving names to each element that A is sent to. Well, A is sent to f of A. That's a very natural name. So with these names, what does A get sent to in the composite?
G of f of a?
Yeah, exactly. G of f of a. F of a is an element of B, and so I can take G and use that to send the element f of a, which is equal to B for some B, to some element of C. So this is the composite function. And in pictures, we can set up very nice pictures like this. Let me do a function composition from A, B, C, and I can compose it with a function to 1, 2, 3, 4, and then I can have a function from 1, 2, 3, 4 to do, re, and mi. And then, so f is the data. When I'm thinking of these finite sets, I can think of a function as just a collection of arrows, essentially. So I'm going to send c to 1, b to 4, and a to 2. That's a function. And then a function, so I can call this the function f. And then g is going to be some function which sends 1 to re, 2 to, or no, 1 to do, 2 to re, 3 to re, and 4 to mi, for instance. And now, of course, I can ask you, what is the image under g composed with f of c? This is going to be equal to what? Yep, this is just do. All that we're doing is we're chaining the arrows, right? So if I try to think about what an element of the first set A goes to under this composition, I just follow it over by the arrow that must exist over to the next set. So C is getting mapped to 1, and then G sends 1 to do. So when I compose the functions, I travel through the whole line all the way to do. How about G composed with f of A?
That'd be re.
Yep, you just follow. A goes to 2 and 2 goes to re. And then similarly, G composed with f of B is going to be, well, B goes to 4 first, and then 4 gets sent to me by G, so me. So here is the kind of abstract definition of function composition. Here is a pictorial representation between some finite sets that I think makes a lot of sense and gives you a good way to imagine what function composition is doing. Are there any questions here?
I have one question.
Sure.
So how do the properties of F and G affect their composition? Like if one is injective and the other surjective, like how does that affect the composite of them?
So that is actually the content of several exercises that I'm certainly going to have y'all prove. There are things like if you know that the composition is surjective, then you must know that the second function must be surjective. If you know that the composition is injective, then you know that the first function must be injective and things like that. So there are a whole collection of relationships that exist when you consider the three functions f, g, and g composed with f. But there are, I mean, yeah, so I don't think that I can give a short answer to that question. Is that okay?
Yeah, thank you.
Yeah. So there are some very strong and nice relationships that do hold, however, and you'll prove some of them on the homework. Okay. I want to also point out that function composition is something that you're very comfortable with when it's in the context of functions from the real numbers to the real numbers, for instance. So let's let f be the function from the real numbers to the real numbers, which is defined by x maps to x squared plus 3x plus 2. In a prior class, you'd probably write this as f of x is equal to x squared plus 3x plus 2, right? These contain the same amount of information, and actually this contains more information because I'm specifying the domain and the codomain, whereas this expression right here is not telling you what the domain and codomain are. But nonetheless, this is probably very familiar. And then let's let g be the function from the reals to the reals given by x maps to cosine of x, which you probably recognize as g of x is equal to cosine x. So my question for you is, what is f composed with g of x, and what is g composed with f of x? Let's start with f composed with g of x. How do I think about this?
Would we, for every value in F, would we just plug in G basically?
Yeah, exactly. So when I think about this function right here, I know that I'm doing g first. So I'm sending x to cosine of x. And then what the function f does is it takes any element and sends it to the square of that element plus 3 times that element plus 2. So then this gets sent to, cosine of x gets sent to cosine squared of x plus 3 cosine of x plus 2. So f composed with g of x is equal to this thing, cosine squared of x plus 3 cosine of x plus 2. So this is on the nose function composition, right? Yeah, I think y'all are comfortable with this. And similarly, what is g composed with f?
Would that be cosine of x squared plus 3x plus 2?
Exactly, cosine of x squared plus 3x plus 2. Because what f does is it sends x to this expression, and then what g does is it takes any value and plugs it in for cosine. And so that's just exactly what we've done here. So when you've got functions from R to R and R to R, you compose them in exactly the same way that you're used to from calculus, for instance. And notice, of course, that composing functions in different orders need not be the same. These are very different functions. But much more importantly than that, for a very general pair of functions, I cannot compose them in either direction. Why is that?
Could you repeat the question, please?
Yeah, so here I'm pointing out, oh, I've got a function from R to R, and I've got another function from R to R. Well, when the codomain of the first function matches the domain of the second function, I can compose them in one particular order. When the domain matches the codomain of the other, I can compose them in another order. And I notice that those two compositions are quite different. The point that I'm trying to get at, though, is that there are a huge number of function compositions where you can only possibly compose them in one way. So for instance, as a as an example that is close to y'all's hearts and should not be taken seriously, if I have one function which takes my class, and then another function which assigns a number out of between 0 and 100, and then there's another function which is, I do some new function from 0 to 100. These are the domains. So here's f, here's g. This could be interpreted, for instance, as assigning to each student their raw score, and then g provides a curve, right? G is some function which takes me from the numbers from 0 to 100 to a different collection of numbers from 0 to 100. Now, it's clear that I can do a function composition. For instance, g, let me write it in the correct way. F, so g composed with f. Now this maps from students to curved scores. But of course, the function f composed with g can't possibly exist, right? Why can f composed with g not, why is this not a function? Why is this not a thing? It's because it doesn't make sense in terms of the domains and codomains. G sends numbers out of 100, 1 through, or 0 through 100, to 0 through 100. And then F sends students to numbers from 0 to 100. There's no way to compose these in this direction because the codomain doesn't match up with the domain, right? I can only compose these functions in one reasonable way. And if the codomain of the first function doesn't match with the domain of the second, then there's no way to compose them. So what I just mean to show by this is that if I'm even able to ask a question, are the two compositions of these functions different? That already means that I'm in a very special situation where I can even compare two different compositions of the same two functions. In general, I cannot compose two arbitrary functions. Right, exactly, Val. I don't mean for this example to scare y'all. I literally couldn't think of a better example to show why you can't compose different functions in different ways. So don't worry. Any questions on this?
Was this a possible hint that our last exam is going to be curved?
No, it is not that either. This is just a way, this is just a natural example of compositions of functions that work in one direction and not in another. I don't know what your grades are yet, so I'm totally agnostic on that front. I'm just asking if this makes reasonable sense. Okay, so the last notion that I want to bring up is how does composition of functions relate to bijections? So here's an example. Here's kind of a motivating example. Let's consider the following functions. Let's consider f mapping from the reals to the positive reals union 0 given by x maps to x squared. And let's consider g mapping from the reals, or the positive reals union 0 to r, given by x maps to the square root of x.
What's that say? What kind of example?
A motivating.
Oh, okay. Thank you.
So, oh, is there a question?
Yeah, what does it say after the positive reals and the for F, or actually both of them?
This part?
Yes.
Positive reals union 0. So really this should be written as r greater than or equal to 0, but r plus. Yeah. Okay. So since the codomain of F matches the domain of G, I can compose them by G composed with F. And since the codomain of G matches the domain of F, I can compose them in the other way. So I can compose these functions in both ways. I should think I can draw a picture here as r greater than or equal to 0, and this is r. And what I can think of is I can think of F as going this way, and I can think of G as going this way, right? No, I've done it backwards, shoot. G is going from this set to this set, and F is going from R to this set, okay? So my question is, what is G composed with F, and what is F composed with G? Let's do G composed with F first. So I start with an element of R, and what does F do to an element of R?
It squares it.
Yep, it squares it, so X gets mapped to X squared. I've kind of traveled via F from R to R greater than or equal to 0 by squaring my number. And now the next step is to act by G. What does G do to a number?
Takes the square root of it.
It takes the square root, so it's going to send X squared to square root of X squared, which is equal to what?
X.
Yeah, just X. Similarly, let's now go the other way. Let's now start on this side. What happens if I take the square root of a number? Well, I'm going to write it in a very similar way. First of all, G is going to send X to the square root of X, and I've restricted my domain such that this is a well-defined thing, right? I'm not taking the square root of any negative numbers because they're not in my domain. So this is a unique assignment. There are no issues with this function. X is going to map to square root of X, and then what is F going to do to this number? Well, it's going to square it. So this is going to be mapped to square root of X squared, which is equal to what again?
X.
X. Exactly. So the point is that I have produced two functions that both are a very special kind of function, namely the identity function. So here, G composed with F equals the identity function on the set R, which means the identity function is just the function from R to R, which sends every element to precisely that element, right? It sends 1 to 1, it sends pi to pi, it sends a million to a million, it sends every number to itself. That's called the identity function. Similarly, F composed with G is equal to the identity function on this other set, on R plus union 0. So in other words, if I start over here and I travel over this set via G, and then I travel back via F, I end up exactly where I started, always. And similarly, if I start over in this set and I travel over here via F, and then I travel back via G, I also end up exactly where I started. Is this relationship between F and G kind of clear, what I've set up? Is there a question about this example? That's correct. These two things aren't exactly the same thing. You're absolutely right that F composed with G and G composed with F are not the same function. And that's why I've written them differently. G composed with F is the identity function on the set of real numbers. Yes. Let me think about this. You're right that I can start with a negative number here and go to a positive number here, and then when I take the square root, I will get something positive back. So I should probably change up this example. You're right. You're right that I made some tragic mistake here, because when I start with a negative number and I square it, I get something positive, and then when I start with something positive here, I'm going to go back to positive. So actually, this whole example, yeah, very good points, and this is a disaster, but a very good point. What I should do is I need to restrict my function f from r greater than or equal to 0 to r greater than or equal to 0. And similarly, I need to restrict g to r greater than or equal to 0 to r greater than or equal to 0. Once I prevent negative numbers from creeping in here, then I will actually have a bijection, or I will be able to compose functions in either way and get the identity back. You're absolutely correct. Yeah, I'm so sorry. This here was a incorrectly worked example, but now here I should have the correct example. Here I should be able to go from r greater than or equal to 0 to r greater than or equal to 0. One way I go over by squaring, x maps to x squared, and the other way I go back by taking square root. X maps to square root of x. And now I should be able to set up a system where f composed with g is equal to the identity function on r greater than or equal to 0, and similarly, g composed with f is equal to the identity from r greater than or equal to 0. Very good point. Thank you. Whew, I had a little heart attack there. Is this better? Okay, so now what I would like to do is formalize this and make this a definition. So definition. A function f from a to b is called invertible if there exists a function b to f, or sorry, g from b to a, such that f composed with, or g composed with f, which is now a function from a to a, is equal to the identity function on a, and f composed with g, which is now a function from b to b, has the property that f composed with g is equal to the identity function on b. So in other words, my definition of invertible is that I set up a function f from a to b. I need to be able to set up a function going in the other direction from b to a, such that when I compose in either direction, I get the identity function. I go back exactly where I end up. Val, you should not be sorry. You should be the opposite of sorry. You pointed out an a huge mistake of mine. Thank you very much for that. I appreciate it. Is this definition okay? Okay, so what I want to now remark is f is invertible if and only if f is bijective. So in other words, this property of being able to find an inverse function, and g here would be called the inverse function to f, this is only possible if the function f is bijective. So now we see that we're connecting the property of bijectivity to the property of having an inverse and having this property on compositions. And so what I briefly want to just discuss before we move on is to discuss how this idea kind of goes. So let's check that if f is bijective, we can define an inverse. So let f from A to B be bijective. And here I'll write it A maps to f of A. So now I want to construct an inverse function. I want to construct g from B to A with the following properties. G is going to send B to the element A such that f of A is equal to B. Now, my point is, in general, for an arbitrary function f, this is not a well-defined thing. This doesn't produce for me a function. But there are 2 points here. One, since f is surjective, what do I get?
All B have an f of A that correspond to them?
Exactly. Since f is surjective, I know that for all B, there exists an A such that f of A is equal to B. So I at least know that trying to send B to the collection of elements that hit it is a non-empty set. So in other words, the 2 things that we need for a function is that every element gets sent somewhere and no element gets sent multiple places. Well, if I want to send B somewhere under this rule, f needs to be surjective. And then 2, since f is injective, what do I get?
If for any arbitrary element of A, it points to the same element in B, they are the same?
Yes, or in other words, this assignment, if I want to assign B to the collection of all A that hit it, that's actually a unique assignment. I'm only assigning B to one single element in A. Since f is injective, there is only one element A such that f of A is equal to B. So here's another way to think about the injectivity and surjectivity conditions, is that if I'm trying to set up an inverse function or a function going the other way, then the surjectivity of f is what allows me to say that my relation G sends every element of B to at least one element of A. And injectivity lets me say that no element of B is sent to multiple elements of A. In other words, injectivity and surjectivity of F are what give us the properties of G that make G a function. Is that okay?
Oh, because then would you like have values of G that would possibly point to, or one value in G that would point to multiple values in F if F
Yeah,
was
I
looking like
can
F
kind of
did?
show an example where this goes wrong, and we can. Oh shoot! I just tore that page like the Hulk. Okay, let's do an example. Let's say this is A, B, C, and D, and let's say this over here is 1, 2, 3, 4. And then let me set up the following function f such that A goes to 2, B goes to 2, C goes to 3, and D goes to 4. Okay. And now what I want to try to think of is, can I define a function g going back the other way such that when I compose them, I get back the identity? So 1, 2, 3, 4, and A, B, C, D. The point is, if I try to assign to an element of, so this is set A and this is set B. If I try to assign to an element, if I try to assign an element of B to the collection of preimages, it won't work. So 1 has no preimages. So my putative function g going the other way doesn't assign 1 to anything. And similarly, if I try to assign 2 to its preimages, well, there are 2 preimages, A and B. So both of those things make a reverse function like not a function, right? Like I can draw a collection of arrows, 2 goes to A, 2 goes to B, 3 goes to C, and 4 goes to D. This is somehow the reverse relation where I've reversed all of the arrows. And now the question is this relation where I reverse all the arrows, is it a function?
No, it couldn't be.
It's not a function for several reasons. It's not a function because 1 isn't being sent anywhere, and it's also not a function because 2 is being sent to 2 different places. But the point is, if I force this function f to be both injective and surjective, then both of those problems go away. And when I reverse all the arrows, I actually get an honest function. So that is why the notions of a bijection and producing an inverse function coincide. And that's not a full proof. This is just a sketch. This is just a description of what's going on. Any questions here? Yeah, so this is an idea to hold on to. Injectivity and surjectivity of F mean if we reverse all the arrows, then that new relation is a function. What an exciting morning. Have a disastrous miss an error in my math. I grade myself harshly for that. Any questions here? So this is kind of a linking up of function composition and bijectivity. Okay, one last opportunity for questions before I move on to section 2.5.
I have one question.
Sure.
So I think last week's homework, Wednesday's homework, was on this. Was that supposed to be this week's homework, or was that intended to be last week's homework?
That's due Wednesday.
Okay, okay.
Yep. So it's both weeks' homework because y'all had a test. Okay. So now we get into 2.5, and I know that not everyone has 2.5, so I'll post I'll post the pages of 2.5 in the Sakai under resources today after I upload this stuff. Okay, so this deals with cardinalities. So the point is the following. In the finite case, or if A and B are finite sets, then there exists a bijection F from A to B if and only if the cardinality of A is equal to the cardinality of B, right? If I want to set up a bijection between two between two sets, those sets had better be the same size. If those sets are different sizes, like say if B is larger, then there's no chance of having a surjective function. And if B is smaller, then there's no chance of having an injective function, right? Do we agree? Thank you. Okay, so the idea to understand cardinalities of infinite sets, we should use bijections. In other words, in the finite case, we were able to know that two sets were of the same size if and only if there existed a bijection. Now we can define for infinite sets two sets to have the same cardinality if and only if there exists a bijection between them. So here's the definition. Sets A and B have the same cardinality if and only if there exists a bijection F from A to B. And now I'll come to another very important definition. A set that has that is either finite or has the same cardinality as z greater than 0, or the positive integers, is called countable. Otherwise, it is called uncountable. Okay. So essentially what I'm saying here is we're going to call a set countable if it either has a bijection with a finite set or if it has a bijection with z greater than 0, or the counting numbers, the positive integers. If it doesn't have a bijection with either of those sets, then it's going to be called uncountable. And I have 4 minutes left, so why don't we, in those 4 minutes that remain, start showing that some sets are countable. So, example. The odd positive integers are countable. So could someone tell me, what do I need to display to show that a set is countable?
You need to show it has a beginning.
Well, according to the definition, I need to produce a bijection, either with the set of positive integers or with a finite set. Right? That's the definition of, yeah, the definition is I need to produce a bijection. So my proof will be finding a bijection. So I define a function f from z greater than 0 to the odd positive integers by sending x to 2x minus 1. Let's make a list. What will 1 be sent to under this map?
Just 1.
Yep, 1 gets sent to 1. What does 2 get sent to?
3.
3. How about 3?
5.
Yep, 5. 4 will go to 7. 5 will go to 9. 6 will go to 11, and so on and so forth. So I need to show, we must show that f is injective and surjective. The function f is injective because it is strictly increasing. Remember we had our definition of strictly increasing functions? Well, strictly increasing functions also work in this setting when you're dealing with positive integers. And this function is strictly increasing because if some integer is less than another integer, positive integer, then its image is less than the image of the larger integer. And secondly, it is surjective because every odd positive integer can be written as 2k minus 1 for some integer k, positive integer k. Okay. So is this, first of all, do we agree that these two statements show that f is actually a bijection because it's an injection and it's a surjection?
Yeah, that makes sense.
Okay. So what we have proven here is that the cardinality of odd positive integers is the same as the cardinality of positive integers. By our definition, where cardinality is precisely can you set up a bijection, there's no way to distinguish the cardinality. Actually, I can say something stronger. The cardinality of the odd positive integers is exactly the same as the cardinality of the positive integers. And that holds even though the odd positive integers are a proper subset of the positive integers. Any questions here?
I have a question.
Sure.
So how do they have the same cardinality when they're a proper subset?
Well, the point is that the definition of cardinality didn't have anything to do with subsets or supersets or anything like that. The definition of cardinality is that two sets have the same cardinality if I can display a bijection between them. And
Okay.
now what you should kind of take from that is that when you have an infinite set, it's quite possible that you can display a bijection between that set and some subset.
So does this definition not hold for infinite sets then? Or is it not like specific enough?
Which definition?
That cardinality can be defined or found simply if there exists a bijection or a function.
No, this is the definition that
Okay.
that two sets have the same cardinality if and only if you can find a bijection between them. So what I am saying is when we take cardinality as our notion of size, then the set of odd positive integers is somehow the same size as the positive integers. And this is what I have just proven. It's a difficult fact to digest, but when your notion of size is called cardinality with the definitions that we gave, then this is just a true fact. I've set up a bijection between these two sets, so they have the same cardinality. Yeah, today's homework will be a subset of the homework due Wednesday, so it'll kind of be a long homework. Okay, this is kind of I mean, it's a simple example in the sense that I don't think any of you disagree with my bijection, but it does lead to a conclusion that might be a little uncomfortable for some of you. This notion that cardinality is our correct notion of size for sets. And when we use this notion of cardinality and the definition that two sets have the same cardinality if and only if there exists a bijection, then okay, the odd positive integers have the same cardinality as the positive integers. That's how it goes. Is that okay? Wow, I've held you all way past. I apologize for that. Of course, I am answering questions today. I have office hours starting at 10:30, so I'm happy to do that. So Luke, cardinality is overwhelmingly the most dominant and important way of measuring size of sets in math. I'm not aware of other ways of measuring size. I'm sure that they exist, but they are probably set theory beyond the set theory that I know. So cardinality is really the overwhelmingly the most common and most reasonable way to measure sizes of sets, at least at the level that we're working in. Yep. Any further questions?
Are there ways to distinguish between different sizes of infinity, like as far as cardinality goes?
Yes, there is. So I will produce for you a set which is uncountable, probably on Wednesday, which means that it cannot be put in bijection with either a finite set or a countable set. It can't be put in bijection with the positive integers. Therefore, it is of a cardinality or size strictly greater. An example is the reals. The reals are going to be an uncountable set. And so this notion of bijections and cardinality can distinguish between the size of infinity of the reals and the size of infinity of the positive integers.
Okay, cool. Thank you.
Yeah, sure.
Oh, by the way, when's your office hours again?
Today at 10:30 are my office hours today. And then there are
Okay,
also office hours tomorrow.
cool. Thank you.
Yeah, absolutely. I will stop recording and